This is lesson 2 in chapter 28. And once again, almost everything that I will be summarizing, most of you would have learned in honors chemistry and or AP chemistry. This is just going to sound a little bit more physicsy as opposed to chemistry, if I can coin a term. And once again, like mentioned in lesson 1, we are pretty confident that this all works for the hydrogen atom and explains the configuration of the hydrogen atom, the energy levels of the hydrogen atom, and by extension, any other particle that only has one electron. We think it explains it pretty well. But we've got a long way to go when we want to go on to the other atoms that have more than one electrons. In any case, every single electron for an atom, thinking particularly of the hydrogen atom, but every single electron is going to have its own address. Just like you might have an address which says which state you live in, but many people live in that state. So you further specify by what city you live in, but many people might live in your same city or town. So you further specify what street you live on, but there could be numerous homes on your street. So then you specify the house number on the street, in the city or town, in the state. And that would be the fourth quantum number if you're following this analogy. Of course, that doesn't mean you're actually in your house all the time, but it's a statement of high probability. The same is true with the quantum numbers. The quantum numbers ultimately are an expression of where an electron is most likely going to be found 90% of the time, with the nucleus at the center of that region of space. So the first quantum number, which is called the principal quantum number, right here, is what we often call the energy level, or the main shell. And this energy level, or main energy level, or main shell, the electron could be in the first main energy level. Typically, that's thought of as the ground state, or the second, or the third, or the fourth. And in fact, with enough zapping of energy from electricity or fire, you can send that electron way, way, way out, many energy levels farther from the nucleus. Or it could leave the confines, the proximity of the nucleus altogether, in which case we're talking about what in chemistry we call the ionization energy, the amount of energy it takes to remove an electron from an atom, thereby creating a cation, a positive ion. Now, as I've joked in the past, if somehow you had a super-duper microscope that could peer at your main energy level, designated by your principal quantum number of 1, 2, 3, 4, 5, you would see that each main energy level is actually made up of one or more subshells. And those subshells are designated by the orbital quantum number. Now, in chemistry, we call those subshells an S, a P, a D, or an F. So, for example, in the first energy level, the number of subshells equals the number of the energy level. So the first energy level only has one subshell. So if this is the principal quantum number, we could say that the second number, the subshell, is known as the orbital quantum number. We called that first subshell the S subshell. The second energy level can have a total of two subshells. And those subshells would be another S, which is different from the first one, as well as a second subshell called the P. Excuse me. The third energy level will have three subshells. It'll have its own S, its own P, and the third one is called a D. The fourth energy level will have four subshells. Another S, another P, another D, and for the first time, an F. If we had enough atoms in the periodic table to need to invoke the fifth energy level, that would have 5 subshells. And that would be an S, a P, a D, an F, and from here on out you just follow the letters of the alphabet, such as G. But that's very seldom needed because by now you don't have enough atoms where you would ever have enough electrons to need a G subshell. Now these letters S, P, D, and F are old-fashioned designations for the subshell and of each of the subshells in each of the energy levels. The more modern quantum number is an actual number, and that actual number begins with 0. It doesn't begin with 1. So an S subshell would be a 0, a P subshell would be a 1, a D subshell would be designated 2, and an F subshell would be designated 3. And so since it starts at 0, where N is the main energy level, the designation of the subshell is N minus 1. So in the first energy level, the subshell would be 1 minus 1, which is 0. In the second energy level, you have 2 minus 1, and the second subshell would be a 1, 2 minus 1, and so forth. Now, the third quantum number is up here, and it's called the orbital magnetic quantum number. And the reason we call it an orbital magnetic quantum number is because if you put this atom with its energy levels inside a very, very strong magnetic field, it sort of slightly pulls apart, it sort of tweaks and splits up each of those subshells actually into what we call orbitals. This effect is called the Zeeman effect. And so if we were looking at some orbital, some subshell, I should say, we'll just call it subshell A, it's possible in a strong magnetic field that we find out that that A subshell is actually made up of 1, 2, 3 orbitals. In fact, in this particular case, I would suggest that this is a P subshell, and P subshells can have 3 orbitals. So S subshells, if we talk about the orbital magnetic quantum number, S subshells only have 1 orbital. P subshells have 3. D subshells have 5. F subshells have 7. And we continue with the odd numbers if they happen to be needed. Now, the actual quantum number designating these orbitals, again, begins with a 0. And then if you had 3 p orbitals and you needed all 3, you would have a 0, a +1, and a -1 as the quantum numbers for your 3 p orbitals. Your 5 d orbitals would be a 0, a +1 and a -1, and a +2 and a -2. So your first electron in a d subshell would have a designation of orbital 0. The next one would be +1, then -1, then +2, then -2 for a total of 5 orbitals. And as you may guess, for the F subshell, it would be 0, +1 and -1, +2 and -2, and +3 and -3 for a total of 7. Now, just for the record, if later on when we talk about the spin quantum number, which limits each orbital to holding a maximum of 2 electrons if they opposite spin, if I multiply all of these number of orbitals by 2 for 2 electrons per orbital, we get the total number of electrons. The total number of electrons in an S subshell can be 2 if they have opposite spin. And since the P subshell has 3 orbitals, you can have a total number of electrons of 6. 2 in the P orbital designated 0, 2 in the +1, 2 in the -1. And then this, of course, is going to be 10 and this is going to be 14. These numbers correspond, by the way, to the number of elements in the S, P, D, and F blocks on the periodic table, which explains the organization or the shape of the periodic table. Now, in general, then, you can have n squared, your n here, that there are n squared states, which would be energy levels, shells, and orbitals, and 2n squared number of electrons possible in each of those main energy levels. Now, the spin quantum number 4, requires an even finer discrimination. In this case, instead of using a strong magnetic field to discern the different orbitals within a subshell, we use a high-resolution spectrometer in order to see and discriminate between the different spectral lines that we would see in each of the orbitals. And we would see that in this fine structure, you would have basically two lines very, very, very close together. And we would say that is because one electron has a positive spin and the other electron has a negative spin, for lack of a better designation. Now, there's some good and bad that goes along with using the word spin. Technically speaking, electrons don't spin because in the end, quantum mechanics considers electrons as being waves, not particles. But the upside might be that since electrons are charged particles, any motion of a charged particle, whether it's orbiting its nucleus or whether it's spinning on its axis, generates a magnetic field. So it does make kind of a connection there. So it's convenient to think about these electrons as spinning, even though that's not necessarily the most accurate way to think about electrons in quantum mechanics. Quantum mechanics is about particles being waves, not actually particles. And so sometimes you use the word spin up or spin down, or we might say a positive spin or a negative spin, or we might say a clockwise spin and a counterclockwise spin. But as far as an actual quantum number is concerned, remember we're talking about quantum numbers, quantum number 4 is either a 1/2 or a -1/2. And that magnitude of the value 1/2 is relatively meaningless. What's really important is whether it's up or down, whether it's positive or negative. So you can see there's lots of weird language when you get into quantum mechanics. But it's one of the most validated and verified and corroborated theories in physics at the experimental level. So, what does this actually look like? Well, we think about these electrons not like being in specific orbits like planets are around a star, but we think about the electrons as having a high probability of being within a region of space. And that region of space can be designated by a mathematical equation, like all regions of space can be designated by a mathematical equation. For example, y equals mx plus b is a mathematical equation that designates a straight line. And there are mathematical equations that designate circles and ellipses, as well as spheres and other three-dimensional surfaces. And so the mathematics of these regions of space, where you have a high probability of finding an electron, typically we use the number 90% probability of finding an electron within that region of space, is designated by what we call Schrödinger equations. And Schrödinger equations are values of psi. And in fact, the value of psi is basically meaningless, but the value of psi squared, and there it is right there, is the actual probability of finding the electron within that region of space. Now, for S subshells, the region of space is a sphere. For p subshells, the region of space is a three-dimensional figure eight. Think of like two balloons that are connected together side by side. Three-dimensional regions of space. And this whole region of space is the place where you would find a p subshell electron 90% of the time. And so let's make a little better figure eight. So if these are two balloons, and try to imagine it in three dimensions, right here in the center, you basically have almost a 0% probability of finding the electron at the very center, because technically that's where the nucleus would be. And you would have a low probability to find the electron outside that pair of balloons, but you would have a 90% probability of finding your electron inside either one of those lobes. And remember we said there are 3 orbitals in a p subshell? Well, one of those orbitals would be the one that I just drew. We could say that's along the x-axis. We could draw another one along the y-axis. And if I had the ability to draw three-dimensionally, the third p subshell would look like a 2 pair of balloons along the z-axis, going into and out of this picture. On Google sometime, look up what a D subshell looks like, and even more complicated, an F subshell. In a D subshell, my favorite orbital looks like an inside-out donut. And of course, there are 5 of those orbitals. And if you had 10 electrons, occupy 2 in each of the 5 orbitals, you would have those 5 orbitals on top of each other. If you had 6 electrons, 2 in each side, in each of the 3 p orbitals, you would have the pair of balloons along the x-axis on top of the pair of balloons on the y-axis, on top of the pair of balloons on the z-axis, all of that on top of the circular s subshell orbital, all of which would have the nucleus at the very center. And you can begin to see that a simple atom is nowhere at all, is not simple at all when you begin to layer all of these orbitals on top of each other as your atoms get bigger and bigger and bigger, with more and more electrons occupying more and more of the orbitals in more and more of the subshells in more and more of the main energy levels. Now, the other thing I should point out here is this graph right here, which shows the probability has a maximum value at some distance of so many nanometers from the center of the atom, which is where the nucleus is. It has a lower probability if it's too close to the nucleus, because it does have a speed, if you will, a centripetal force as it whizzes around the nucleus, or I should say as you have a high probability of finding it in a region of space apart from the nucleus, as well as a smaller probability as you get farther away from the center. And so in general, right here, quantum mechanics predicts a most probable electron distance from the nucleus. Now, the Pauli exclusion principle basically says that no 2 electrons for a given atom can have exactly the same address, exactly the same set of quantum numbers. Remember, n begins with a 1, 2, 3, 4, 5, 6, and so forth. L begins with a 0 and continues 1, 2, 3, 4, 5, 6, and so forth. M sub L begins with a 0 and then goes +1, -1, +2, -2, +3, -3, and so forth. And M is either a +1/2 or a -1/2. These are the actual quantum numbers. And again, we're speaking in terms of the high probability of finding an electron at any moment. Now, one of the powers of this quantum model is it correctly explains very, very well why the periodic table is laid out the way that it is. Well over 100 years ago, Russian Dmitry Mendeleev, who there is a picture of him on the side wall in my room, and if you look at that picture, he looks very, very much like I did with long hair way back when I was maybe in my senior year or first year out of college. And Dmitry is famous for never cutting his hair except in January. And in any case, what he did was he organized the periodic table in such a way that all the elements that had similar chemical properties were all in at the same column. He actually used a row, and then we flipped it around to be a column, and then the next column, let's fix that again. The next column would have all the elements in this column would have similar properties. And of course, we now know the reason they had similar properties. Let's say that this element is lithium and sodium and potassium and so forth. They all have similar chemical properties because they all have a similar outer shell electron, just one valence electron in the outer shell, which is why it combines with other elements in a very, very similar way. And in this column, you would have 2 valence electrons. Way over on the right-hand side, you'd have your inert gases, which turns out to have their outer main energy level, at least the S and P subshell, completely filled. And because they're completely filled, they don't want to lose or gain any electrons, and they have a tendency to be very inert. We often call them the noble gases. Here's the word inert and noble gases. So in a vertical column, Dmitry Mendeleev, his were horizontal rows, you have very, very similar chemical properties because they have a similar electronic arrangement from the outside looking in. In other words, valence electrons. The other thing that Dmitry Mendeleev's periodic table did so well is it left some vacancies, some spaces where he didn't find any element. The next element that they knew about didn't go where in the next consecutive spot, but had to skip a spot. And so he predicted that that element would be found there. And sure enough, those elements were found. And if you go to your chemistry book, we can talk more about that, but that's not the purpose right now in here. I will say that one of those elements was germanium, which was discovered in the country of Germany. And the other element was gallium, which was discovered in the country of France. The Latin word for France is Gaul. In fact, in Caesar's Gallic Wars, the opening lines in Latin of Caesar's Gallic Wars are Gallia est omnis divisa in partes tres. All Gaul is divided into 3 parts. And I'm sure you're glad to know that. Now, a couple of other important applications. The first has to do with X-rays. I mentioned here that X-rays are kind of opposite of the photoelectric effect, thinking again of symmetry, which I mentioned in an earlier screencast. You might recall that if you shine light, intense light, onto a piece of metal, electrons will jump off that metal. We call those photoelectrons, and this effect is called the photoelectric effect. It's actually something that's discussed in chapter 27. Well, if we reverse that whole thing, more or less, and in this time we shine or stream or shoot high energy electrons onto a piece of metal, we get high energy photons coming off, just the opposite of the photoelectric effect. And those high energy photons are X-rays. And those X-rays turn out to create, if we graph them over here, kind of a fingerprint for every single kind of metal. So you can do an X-ray analysis on a particular kind of metal if you're not quite sure what that metal is. Let's say you've found that at a crime scene or something like that. Now, the cool thing about these X-rays is typically in chemistry, we think about just that outer shell electron jumping out to a higher energy level and then falling back, which we talked about in lesson 1 of this very chapter. But in this case, what if that high energy electron that we're shining at the metal penetrates the metal and goes to an inner shell and knocks an electron out? Well, then as electrons fall back to that vacancy or that opening from one of the higher energy levels, you get sort of a cascading effect, if you will, as electrons tumble down to fill up the openings. And so you can get multiple peaks like here and here. And so these multiple peaks are called lines. So this would be a line, this would be a line. And for example, if you look at the K alpha line, that would be an electron falling from the second energy level down to the first energy level. If indeed an electron all the way down at the very first energy level got jarred loose by a high energy electron, then an energy level in the second energy level filling in that space would create a X-ray line on that particular graph. And that's called an alpha line, falling from the K down to the first. Well, why do they call it the K? Because 100 years ago, the first energy level was called a K, the second energy level was called an L, the third energy level was called an M, the fourth energy level was called an N, and you just go right on down the alphabet. That is ancient history. You might also recall from lesson 1 in this chapter that only those electrons that fall back to the second energy level, when they are outer shell electrons, produce spectral lines in the visible region. Now, these are X-rays, of course, so they're not going to be visible. But that's because there are many shells of electrons in metals. We're not talking about an outer shell electron being ejected, but we're talking about an inner shell electron. So if a high speed electron, a high energy electron penetrates several shells all the way down to the second energy level and knocks an electron out, then maybe some electron in the third energy level falls into that vacancy. We call those L lines because L represents the second energy level. And the first one would be an alpha, the second one would be a beta, the third one would be a gamma, and so forth. And we can also see that this helps us to determine the atomic number, which is designated by the letter Z. We can estimate the amount of energy that's involved, and you recognize some of these terms from lesson number 1. Now, by the way, it is not uncommon on an AP exam, this would probably be AP Physics 2, to have a question about a graph like this one in one of the essay questions. And here you can see that this Moseley plot by Henry Moseley, again more than 100 years ago, graphing the atomic number Z, which is basically the number of protons, versus the square root of 1 over the wavelength, which we can determine from the frequency or vice versa, produces a straight line. When you get a straight line in a graph, you know that there's a pattern, and if there's a pattern, that means there's a physics phenomenon that you need to investigate. Now, the last thing or application here has to do with lasers. And we talked about lasers way back in chapter 24. Laser stands for the light amplification from the stimulated emission of radiation. It's an acronym, just like sonar is an acronym. And there are lots of acronyms that we use in physics. And so I'm not going to talk about how if we have a nucleus might have electrons here, and let's say we have another electron here, and let's say we zap this with some energy, fire electricity, and one of these electrons jumps out to a higher energy level, and then we have a photon of light coming in, and that photon of light, this is going to have to be a photon, so I'll make a wavelength symbol there. If it happens to hit that electron, this electron will fall back down to its ground state, or jump back in the terminology of your book, and it'll give off a photon matching the photon that was incoming. So whoops, didn't mean to do that. So here is my first photon there. Here's my second photon as my energized electron falls back, and these two photons are going to have the same wavelength. And if they can be put in phase, which means their amplitudes and their troughs are identical and match up, you've now doubled their energy. And it's going to be very, very focused. If you have a high energy laser, you can shine it on the moon, and that beam of light won't spread out more than maybe a kilometer by the time it gets all the way to the moon. And here's a diagram that tries to show that. And of course, we have all kinds of applications of lasers, more and more and more just about every year. And one example of a laser that I'm happy about are the kinds of lasers they use to improve your vision. I've had some laser work done in my eyes, as well as I've had entire lens replacements. I have bionic lenses under my corneas rather than my original lenses. And because of that, I no longer have the cloudiness of eyes, which prevents me from seeing colors in all of their beauty, called cataracts, and I no longer have any astigmatism, and I no longer have my farsightedness. So that's really, really nice. I've also had lasers used to help to repair just a little bit of retinal separation in the back of my eyes. Well, that was more cryogenic. But the lasers help to also clean off any debris or scum that might form over an artificial lens as well. Of course, nowadays, not only are we using them for cutting and etching metal, but they're also being used and have been for some time. Just very little of this is known because it's classified, but lasers have been used to knock out satellites in outer space. That's another story I could tell you about later. This concludes chapter 28.